In 1969, a single company in Beaverton, Oregon, controlled 75% of the global oscilloscope market. 24,000 people worked on a 300-acre campus surrounded by Douglas fir, building the instruments that every electrical engineer on Earth needed to do their job. If you were designing a circuit, debugging a radar system, testing a transistor, or building the guidance computer for a moon mission, you were looking at a Tektronix screen. A steady green trace on a phosphor tube, rock solid and measurable for the first time in the history of electronics, because a Reed College physics graduate named Howard Vollum had figured out how to make it hold still. On October 15, 2007, Danaher Corporation offered $38 per share for the entire company. 90% of shareholders tendered within 5 weeks. The TEK ticker vanished from the New York Stock Exchange. Danaher folded Tektronix into its portfolio, spun it into a subsidiary called Fortive, and Fortive spun it again into a holding company called Ralliant. Today, roughly 3,000 people work where 24,000 once did, and most engineers under 40 have never heard the name. This is the story of the company that gave Silicon Valley its eyes, and how the industry it created looked the other way. You're watching Tech District, where we pull apart the companies that built the electronic world, down to the circuit board and the engineer who designed it. If oscilloscopes and Oregon and 24,000 jobs is your kind of story, subscribe and hit like, because the rise here is just as strange as the fall. Howard Vollum was born on May 31, 1913, in Portland, Oregon, and grew up in the Selwood neighborhood on the east side of the Willamette River. He attended St. Agatha's Grade School and St. Stephen's High School before spending a year at the University of Portland, then transferred to Reed College, one of the most demanding small colleges in the country, and graduated in 1936 with a degree in physics. While still an undergraduate, he built his first oscilloscope. That fact matters because of what oscilloscopes were in the 1930s. Every scope on the market used what was called a free-running sweep. The electron beam inside the cathode ray tube traced a line across the screen at a fixed rate, and the signal you were trying to measure was layered on top of it. The problem was synchronization. The sweep and the signal were not locked together. The image drifted, wobbled, and blurred. Engineers adjusted a knob labeled sync and tried to coax the trace into sitting still long enough to take a reading. Two people looking at the same circuit on the same oscilloscope could get two different numbers. It was less measurement than negotiation. The dominant name in the business was Alan Dumont, who had been building cathode ray tubes and oscilloscopes in New Jersey since the 1930s. Dumont's instruments were expensive, often costing well over $1,000, and their sweep circuits suffered from the same instability as everyone else's. The entire oscilloscope market was small, specialized, and waiting for someone to solve the fundamental problem that made every instrument on the market unreliable. After Reed, Vollum worked as a radio repair technician and then took a job at a small shop on Southeast Foster Road in Portland called Murdoch Radio and Appliance, owned by a young entrepreneur named Jack Murdoch. Murdoch had opened the business in 1936 with help from his parents. He was 19 years old. He never went to college. He was practical, quiet, and good with customers. Vollum was meticulous, obsessive, and good with circuits. They got along immediately. Then the war came. Vollum was drafted in 1940 and received a Signal Corps commission in 1941. The Army sent him to Christchurch, England, where he worked on high-resolution radar, the kind of classified work that earned him the Legion of Merit. Later, back in the United States, he developed mortar-locating radar at Evans Signal Laboratory in New Jersey and received an oak leaf cluster. The war taught Vollum two things. First, new circuit techniques for high-speed electronics that barely existed before 1940. Second, every radar station in England was fighting with its own test equipment. The oscilloscopes were terrible. He came home with the answer already forming in his mind. On January 2, 1946, 4 men incorporated a company called Tekrad in Portland, Oregon. Howard Vollum, Jack Murdoch, Miles Tippery, and Glenn McDowell. Each put in $2,600, Total starting capital was $10,400. Within a month, they renamed it Tektronix. They set up in a basement workshop on Southeast Foster Road, the same street where Murdoch had run his radio shop before the war. Vollum designed a prototype oscilloscope that sprawled across an entire workbench, then refined it with machinist Milt Bave, engineer Frank Hood, and circuit designer Logan Belleville into something that could ship. They called it the Type 511. It was ready by May 1947. 50 pounds, $795, 10 megahertz of bandwidth, 33 vacuum tubes, and it did something no commercial oscilloscope had ever done reliably. It triggered. Vollum's sweep circuit did not free run. It waited. It sat silent until the incoming signal crossed a voltage threshold the operator had set, and only then did it fire the electron beam across the screen. The result was a trace, locked to the signal like a photograph. Stable, repeatable, measurable. For the first time, an engineer could look at a waveform and trust what they saw. The story everyone tells is that Howard Vollum invented triggered sweep. The documented record is slightly more complicated. Triggered time-based circuits existed in specialized laboratory instruments before 1946. What Vollum and his team did was make the concept work inside a compact, affordable, general-purpose oscilloscope that an ordinary engineer could buy and operate. Whether that makes him the inventor or the person who found the right application is a question reasonable people can answer differently, and honest history holds both readings at once. What is not in dispute is the result. Alan Dumont, the dominant oscilloscope manufacturer in America, examined the Type 511 at an electronics trade show. His own two-piece oscilloscope cost $1,800 and could not hold a stable trace. Vollum's cost less than half that price and drew a clean line every time. First-year sales of the 511 came to $27,000. By 1948, that number reached $257,000. By 1950, Tektronix reported $1.2 million in revenue, with orders backlogged 6 to 12 months. 16 employees in 1947 became 109 by 1950. Something much larger had begun to take shape. But growth exposed a dependency that could have destroyed the company. Every oscilloscope Tektronix built required a cathode ray tube, the phosphor-coated glass envelope where the electron beam drew its trace. Tektronix did not make cathode ray tubes. They bought them from RCA and Dumont. Supply was unreliable. Quality varied batch to batch. The heart of the oscilloscope was in someone else's hands. In late 1952, Vollum made a decision that looked reckless. He assigned 3 people to solve the problem from scratch: Darrell Pennington, a biochemist; Jean Delord, a physics teacher; John Griffin, a glassblower. None of them had ever built a vacuum tube. Vollum sketched a helix-shaped accelerator design that could improve electron beam focus and let them figure out the rest. They did. Within 2 years, Tektronix was manufacturing its own CRTs, and the quality was superior to anything they had been buying. The company now controlled the most critical component in its product. No supplier could hold them hostage again. The business side ran on Jack Murdoch. Vollum would vanish into the lab for days. Murdoch hired the salespeople, signed the leases, and kept the books honest. Colleagues described him as unpretentious, soft-spoken, and scrupulously fair. He ran a side business growing Asiatic lilies at a place called Oregon Bulb Farms. He flew his own plane and held a Piper aircraft distributorship out of Pearson Field in Vancouver, Washington. In 1971, Jack Murdoch died in a float plane accident on the Columbia River. He was 53 years old. His will created the M.J. Murdoch Charitable Trust, which still funds science and education across the Pacific Northwest today. The company lost the man who had balanced its books and its temperament in equal measure. Dallas, the 13th employee and the company's first sales manager, had been building a national network of field engineers since 1948, hiring people for technical ability rather than sales experience, and embedding them in the regions they served. That infrastructure kept revenue growing even through the grief. The company buried its co-founder and kept building oscilloscopes. The CRT breakthrough unlocked what came next. In 1954, Dick Rager led the design of the Type 535, the company's first plug-in oscilloscope. The concept was modular. One mainframe and a set of interchangeable vertical and horizontal plug-in units that slid into the front panel. Pull one out, slide another in, and the same instrument became a different tool. A standard vertical amplifier could be swapped for a spectrum analyzer plug-in, a transistor curve tracer, a differential amplifier, or a sampling head. One purchase covered a dozen applications. This was not an obvious idea at the time. Test equipment had always been a fixed instrument. You bought an oscilloscope for one job, and when you needed a different measurement, you bought a different instrument. An electronics lab could easily spend tens of thousands of dollars assembling a bench full of single-purpose tools. The plug-in architecture asked engineers to rethink what an oscilloscope was, and they answered by buying everything Tektronix could manufacture. The 535 stayed in production for 18 years. In 1955, Dave Barton and Bob Shand designed the Type 545, which pushed bandwidth to 30 MHz and added dual time bases. An engineer could trigger on one part of a signal and then examine a delayed section of it with forensic precision. The 545 cost $1,550 in 1959 and became the standard laboratory oscilloscope in America. If you walked into an engineering lab at MIT, Bell Labs, or the Jet Propulsion Laboratory between 1955 and 1974, the scope on the bench was almost certainly a Tektronix 545. By 1956, Tektronix had passed Dumont as the leading oscilloscope manufacturer in the world. The plug-in franchise was the reason, but it also set a pattern that would matter later. The modular architecture assumed a mainframe, the mainframe assumed a cathode ray tube, and the cathode ray tube assumed analog. Every plug-in sold reinforced the analog ecosystem. 2 decades later, when Hewlett-Packard arrived at Westcon with instruments that outpaced the 7000 series, the roots of that problem were already deep in the ground. The Cold War handed Tektronix a blank check. The United States military needed oscilloscopes for field use and contracted for ruggedized versions of the 453, a 50 MHz portable scope built to survive rough handling and still hold calibration. NASA needed scopes at launch facilities, tracking stations, and mission control. Every defense contractor designing radar, guidance systems, or communications equipment ordered Tektronix instruments for the test bench. The real accelerant was the semiconductor. When the transistor arrived, and then the integrated circuit, the number of electronic signals that needed testing multiplied by orders of magnitude. Every new fabrication plant needed oscilloscopes by the rack. The more chips the industry built, the more scopes it consumed. Tektronix sold the shovels in a gold rush that never stopped. The numbers tell the story without commentary. Tektronix reported $1.2 million in sales in 1950, $43 million in 1960, $148 million by 1969, a 12,000% increase in 19 years. The products kept expanding with the market. In 1961, Tektronix introduced the Model 321, possibly the world's first practical, fully portable oscilloscope, able to run on rechargeable batteries in the field. In 1964, the Model 564 became the first mass-produced analog storage oscilloscope, capable of holding a waveform on the screen for an hour instead of watching it flash and vanish. These were not incremental improvements. Each one opened a category that had not existed before. Field service technicians could now carry a Tektronix scope to a broken transmitter on a mountaintop. A researcher studying a one-time transient event could finally capture it. On May 1, 1959, Tektronix moved into a new headquarters campus in Beaverton, Oregon. 313 acres, purchased through the Employee Retirement Trust and leased back to the company. By 1976, nearly 10,000 people worked there. Tektronix was Oregon's largest private employer. In 1975, the company joined the Fortune 500, ranked 457th, with $336.6 million in sales. The culture matched the engineering, profit sharing for every employee, Open cash boxes in the cafeteria, honor system. No reserved parking, not even for the president. Free coffee. Open component shelves where engineers could take parts for personal projects without filling out a requisition. Vollum believed that nearly everyone wants to do good work if you give them room and responsibility instead of rules. In 1978, Tektronix was named one of the 100 best companies to work for in America. First Tech Federal Credit Union began its life as Tektronix Federal Credit Union, serving the people who built the instruments. $1 billion in annual sales was within reach. In 1981, Tektronix crossed the line. Over 24,000 employees worldwide, 15,000 of them in the Portland area. 75% of the global oscilloscope market. The Beaverton campus was a company town built by engineers for engineers. The Type 545 earned its reputation through 20 years of daily use. The plugins clicked into the mainframe with a mechanical precision that told you the tolerances were right before you touched a probe. The dual time bases let you trigger on a fast edge and examine a delayed portion of the waveform as though time itself could be paused and expanded. Every reading was calibrated, every measurement repeatable. The 545 was not a delicate research instrument that lived in one room. It went to MIT and it went to Lockheed. It sat in university teaching labs and semiconductor fabs. It was produced from 1955 to 1974, and working units still sell today on collector markets for $300 to $800. People buy them to use, not to display. 6 decades after production ended, the traces still hold. The Type 71004 was the end of a different road entirely. Introduced in 1978, it achieved 1 gigahertz of bandwidth with a rise time under 350 picoseconds. No other analog oscilloscope on Earth could touch it. The technology that made it possible was a microchannel plate cathode ray tube, developed over 7 years under project leaders Val Garutz and Gene Andrews. The plate was a thin disc of glass, riddled with millions of microscopic channels, each one acting as an electron multiplier. The beam entered weak and emerged amplified, producing a visible trace at sweep speeds no conventional tube could handle. The mainframe alone cost $14,400 in 1980. A fully equipped system ran over $21,000. In today's currency, that is more than $85,000 for a single oscilloscope. The microchannel plate degraded with use, and a continuous signal could burn the screen. The instrument carried a built-in timer that shut down the beam after 20 minutes of sustained operation. Engineers treated it with the care normally reserved for optical equipment. It was not a workhorse. It was a monument to what analog measurement could achieve when taken to its absolute limit. And like all monuments, it marked the end of something as much as the height. Tektronix also made instruments beyond oscilloscopes. The Tektronix 4014 graphics terminal, built around the company's proprietary direct view storage tube, became the standard for computer-aided design and scientific visualization in the 1970s and early 80s. Universities, government labs, and engineering firms across the country rendered their data on Tektronix screens. The 4014 protocol outlived the terminal itself and is still emulated in modern software. The Silicon Forest grew from Tektronix soil. Norman Winningstad founded Floating Point Systems. Tom Bruguiere started Mentor Graphics. Planar Systems spun out. InFocus spun out. Between 1946 and 2000, more than 60 companies were founded by people who had learned engineering, manufacturing, or management inside Tektronix's walls. High-tech employment in the Portland area nearly doubled from 34,000 to 61,000 between 1988 and 2000. Tektronix donated land for the Oregon Graduate Center, seeding the research institution that attracted further investment and further talent. The company did not just make oscilloscopes. It made the ecosystem that built Oregon's technology economy. Even the culture produced unexpected legacies. Ward Cunningham, who would go on to invent the wiki, the collaborative format that powers Wikipedia, developed his ideas about software while working at Tektronix in the 1980s. The company's atmosphere of open shelves, shared knowledge, and informal collaboration was not just good for morale, it shaped the way at least one of its engineers thought about how human beings should share information. But the seed was already in the soil. In 1973, an engineer named Hiro Moriyasu led a team that built the P7001, a digitizer plugin for the 7704A mainframe. Moriyasu had joined Tektronix in 1956 and would hold more than 20 patents before he left in 1986. The P7001 converted analog signals to digital data, stored them in electronic memory, and displayed the captured waveform on the screen. It was, by any honest definition, a digital oscilloscope. Tektronix filed the patents, listed it in the catalog as a specialty product, and turned its attention back to analog. The analog business generated margins that funded everything else. The P7001 sat on a shelf. Meanwhile, the company had expanded into graphics terminals, where it held 51% of the market. It had acquired the Grass Valley Group, a maker of television broadcast switching equipment. It built computer workstations running its own Unix variant. It developed solid ink color printers under the Phaser brand. Revenue from oscilloscopes was still the foundation, but the company's attention was scattered across half a dozen product lines, each with its own division, its own budget, and its own definition of the future. Every one of those bets was about to come due. The 1980s arrived, and the ground shifted under all of them. The warning signs had been visible for more than a decade if anyone had been willing to read them. In the late 1960s, Hewlett-Packard had introduced its 180 series oscilloscopes, which were compact, modern, and competitive at bandwidths Tektronix considered its territory. The response inside Tektronix was close to panic. Howard Vollum personally drove the development of the 7000 series, mandating mid-project that the plug-in height be reduced from 7 inches to 5.5 to match Hewlett-Packard's dimensions. Engineer Oliver Dalton later called the decision traumatic. It forced a redesign of every push-button, cam switch, and relay in the instrument and delayed the project by roughly a year. When the 7000 series finally shipped at Westcon in August 1969, Tektronix announced the 7504 at 75 MHz and the 7704 at 150. Competitors had already announced instruments at 250. The company had spent years catching up and arrived behind. By the 1980s, that pattern had hardened. Japanese manufacturers were shipping oscilloscopes at half the price, good enough for most bench work, and priced to move in volume. The personal computer revolution meant engineers now needed logic analyzers, protocol decoders, and software debugging tools alongside their scopes. Tektronix had products in several of these categories, spread across divisions that each guarded their own budgets and their own margins. The graphics terminal business collapsed first. Market share fell from 51% to 26% between 1979 and 1984. Earnings across the company dropped more than 40% in the same window. The oscilloscope division saw no reason to cannibalize the analog franchise with digital instruments when analog was still profitable. The terminal division was being overtaken by workstation manufacturers. The printer division was fighting a price war with Hewlett-Packard that it could not win. In 1985, Tektronix acquired a company called CAE Systems for its computer-aided engineering software. By 1988, the estimated total loss from the failed venture had reached somewhere between $150 million and $225 million. They sold it to Mentor Graphics, their own spin-off, for $5 million. That same year, Tektronix reported its first-ever annual loss, $16.7 million. The recovery would cost the company far more than anyone in Beaverton was prepared to pay, and it would come not through invention, but through subtraction. In 1987, the stock sat at $31 a share. David Friedley became president and eliminated 2,500 jobs over 2 years. In 1990, the stock hit $12.75, a 14-year low. The annual loss reached $92.5 million. Robert Lundeen and William Walker took direct operational control. 1,300 more people were let go. 24,000 employees in 1981, had become roughly 12,000 by 1991. In 1992, George Soros bought 13.9% of the company and demanded 3 board seats. Delbert Yocham, a former Apple executive, was brought in as president. In 1993, Tektronix took a $150 million restructuring charge. Net loss for the year was $55 million. 800 more positions disappeared. Then came the dismantling, piece by piece. They sold the Grass Valley Group to Thomson. They sold the entire color printer division, the phaser line, and 2,100 employees in Wilsonville to Xerox for $950 million. They sold the video business. By the year 2000, CEO Rick Wills had stripped Tektronix back to its core. It was a measurement instruments company again, the thing it had been in 1946, with $900 million in annual sales and 4,100 employees. The stock recovered. Market capitalization reached $3 billion by April 2006. None of it was enough. On October 15, 2007, Danaher Corporation offered $38 a share. Total value, $2.85 billion. 90% of shareholders tendered. On November 21, 2007, the TEK ticker disappeared from the New York Stock Exchange. Danaher cut worldwide headcount by roughly 10% within the first year. Production began shifting. The company that Howard Vollum and Jack Murdoch had built in Portland, Oregon, became a line item inside a Washington, D.C. conglomerate. Danaher later spun it into Fortive in 2016. Fortive spun it into Ralliant in 2024. 3,000 employees remain. The arithmetic is cold. A company that crossed $1 billion in annual sales in 1981 and employed 24,000 people sold for less than 3 times its peak revenue. Howard Vollum died on February 3, 1986, in Portland, 2 years before the first loss. Jack Murdoch died on the Columbia River in 1971, a decade before the peak. Neither man saw the sale. But the company is not what survived. What survived is everything the company touched. The Vintage Tech Museum sits on the Beaverton campus, where 24,000 people once worked. Inside, volunteers preserve thousands of instruments spanning every era of Tektronix history. Retired engineers lead tours for robotics teams and summer camp students. A Type 511 oscilloscope, built in the late 1940s, still turns on when you flip the switch. The trace still holds. Dave Brown, a former Tektronix vice president who worked at the company from 1976 to 2010, serves as the museum's president. He describes the collector base simply. Tektronix has very loyal collectors. Online, an encyclopedia called TechWiki documents every Tektronix instrument ever manufactured. Enthusiasts photograph, measure, repair, and catalog machines that went out of production decades ago. People do not build encyclopedias about things they feel neutral toward. They do it because the machines were that good, because the engineering was honest in a way that survives the company that produced it. The Silicon Forest still stands. Intel arrived in Oregon in 1976, drawn in part by the engineering talent pool that Tektronix had spent 30 years cultivating. Mentor Graphics, Floating Point Systems, Planar Systems, InFocus, and dozens of other companies trace their origins to engineers who learned their craft under Tektronix's roof. Portland's technology economy is Tektronix's child. The company that seeded the Silicon Forest is the tree nobody remembers planting. First Tech Federal Credit Union, founded as Tektronix Federal Credit Union, still serves members across the country. The M.J. Murdoch Charitable Trust, endowed by the estate of the man who died on the Columbia River at 53, has distributed more than $1 billion to science and education across the Pacific Northwest since 1975. Jack Murdoch's money is still building the future he did not live to see. And every oscilloscope made today, by every manufacturer on Earth, uses triggered sweep. In 1946, Howard Vollum sat in a basement workshop on Southeast Foster Road in Portland, Oregon, and solved a problem that every engineer in the world had been fighting for decades: how to see electricity clearly. His triggered sweep circuit snapped the wobbling blur on a cathode ray tube into a clean, stable line. For the first time, a human being could look at an electronic signal and know exactly what it was doing. That line, that green trace on a phosphor screen, the same steady glow still burning in the Type 511 at the Vintage Tech Museum in Beaverton, became the foundation of the entire electronics industry. Every transistor tested, every integrated circuit debugged, every microprocessor brought to life, every signal analyzed in every laboratory in the world for the next half-century, passed through a descendant of the instrument Howard Vollum, built in a Portland basement with $10,400 and 4 friends who believed the world needed a better way to see what electricity was doing. Every oscilloscope sold today carries Howard Vollum's triggered sweep inside it. Tektronix gave an entire industry the ability to see what it was building, and the industry repaid them by forgetting who made the instrument. If you ever used a Tektronix oscilloscope, if you worked on the Beaverton campus, if you were one of the 24,000, drop a comment below. Tell us the model, the year, and whether it still turns on. The people who used these machines know more about what was lost than the people who sold the company. Subscribe to join the archive. We have the story of another American technology empire coming next, and you will not want to miss how it ends.